All right, welcome. Today, we're diving headfirst into a really cool corner of mathematics. We're going to uncover an incredible infinite toolkit that lets us solve equations that, honestly, seem impossible, but they describe some of the most complex stuff in our universe. So let me start with a question. What could the sound of a cymbal and the heat moving through a car's piston possibly have in common? I know, it sounds like a weird riddle, right? But the answer is actually hidden in a specific type of math problem. And by the end of this, you're going to see exactly how these things are connected. Okay, so first things first, we need to understand the challenge we're up against. See, not all equations are created equal. Some of them, well, they're just plain stubborn. Think about it. Some of the math problems you've seen before are pretty straightforward. They're like a simple lock with a key. But in physics and engineering, the equations that describe the real world, they fight back. They're way more like a complex safe, where the combination is constantly changing. Okay, let's make this real. On the left, we've got an equation that's pretty easy to handle. The numbers that control it, the coefficients, are just 2 and 1. They're constant, they don't change. It's predictable. But now look to the right. See those P of x and Q of x things? That means the rules of the game are changing depending on x. It's like trying to solve a puzzle where the pieces literally change shape while you're holding them. That's what makes these equations so stubborn. So that's the million-dollar question, isn't it? Our normal methods just don't work here. But we can't just give up, because these equations are absolutely everywhere in science. We need a totally new way to think about this. We need a more flexible tool. And that brings us to the hero of our story, an idea called a power series. I want you to think of it less like a single tool and more like an infinite Lego set. So what is this Lego set? A power series is basically just a polynomial that goes on forever. And here's the genius of it. Instead of trying to find one single perfect pre-made answer to our equation, we're going to build the answer piece by piece. Each of those simple little terms you see is like one single Lego brick. Let's see this in action. Say we want to build the smooth wave of a cosine function. Our very first brick, our first guess, is just y equals 1. It's just a flat line. Yeah, not a great copy of a cosine wave, right? But you got to start somewhere. Okay, now let's add the next Lego brick in the series. Watch this. We add the next term, and suddenly it's got a little downward curve. See that? Our flat line is already starting to hug the real shape of the cosine function, at least right there in the middle. It's getting better. And now, watch what happens when we click the next piece into place. Boom. Our approximation snaps even closer to the real wave, and it holds that shape for even longer. This is the magic of the whole thing. If we keep adding enough of these simple little Lego bricks, we can build a perfect replica of almost any complex function. So the actual process is surprisingly clear. First, you just assume your answer can be built with these infinite Legos. Then you plug that whole idea back into the original stubborn equation, and when you do that, it lets you figure out the exact shape of each Lego brick you need. Those are the A values. You just find the pattern for the bricks, and boom, you've built the solution from the ground up. But you know, in every good story, there's always a plot twist. What happens when our equation hits a point where the math itself seems to just break? We call these singular points. You can think of them as these little mathematical black holes. At one specific value of x, some part of our equation might suddenly try to make us divide by 0. And as you know, that's a huge no-no in math. The equation just goes haywire. And at that point, our standard Lego set, it just falls apart. So, to get past these really tricky spots, our toolkit needs an upgrade. It needs a power-up. And that's where something called the Frobenius method comes in. Now, what's really cool here is the tiny but super powerful addition right at the front. You see that x minus x0r term? That little thing is like a special adapter for our toolkit. It lets our Lego set method work even at those messy singular points. It's a total game changer. And what's great is that this upgraded method basically gives us a cheat sheet. That special R value in our adapter, we solve for it, and depending on what we get, this table tells us the exact recipe to follow to build our solution. It walks us through 3 different scenarios, showing us exactly what our answer needs to look like, even when things get really complicated. Okay, so now we've got our super-powered infinite toolkit. It's time to use it to take on one of the great boss-level equations in all of physics. This is the Bessel equation. And yeah, I know, it looks intimidating, but trust me, this single stubborn-looking equation is one of the most important in all of science. It describes an incredible number of things in the world around us. And here is the really amazing part. When we use our powerful Frobenius toolkit to solve this monster of an equation, we don't just get some formula. We actually discover a whole new family of functions that were hidden inside it all along, the Bessel functions. So what on earth are Bessel functions? Well, they're basically the mathematical alphabet for anything that wobbles, waves, or vibrates. Remember our question from the beginning? The vibration patterns on a symbol, the way heat spreads out in a cylinder? Yep, both of those are described perfectly by these functions. And that is the ultimate payoff. We started with this abstract, stubborn equation. We built this incredible infinite toolkit to solve it, and we ended up with the precise mathematical language needed to describe these beautiful, complex patterns that we see and hear every single day. It really makes you wonder, doesn't it? By creating these incredible mathematical tools, we literally gain the power to translate the universe's most complex secrets into a language we can finally understand. What else is out there, just waiting for us to find it?